Okay, move on to ultimate capacity of group piles in saturated clay. So the figure in 9.47 shows a group pile in saturated clay. So using that figure, one can estimate the ultimate load-bearing capacity of group piles in the following manner. So we have here following steps. So we have to determine our summation of Q sub U equal to this equation where Q sub P is equal to this, and C sub U, which is our under equation of the clay at the pile tip. From Q sub S, which is equal to this equation, we can have the value for the summation of Q sub U equal to this expression. You simply have to just substitute Q sub P and Q sub S. So this is the figure that was described in our discussion a while ago. So we have here the ultimate capacity of group piles in clay. So our Q sub S here for our under equation of clay at the pile tip. So our Q sub S equal to this. So we simply have now this expression. So we have our Q sub G, that is the ultimate load acting on the pile cap of our group piles. And we have to take note the location. This is our L sub G. This is our B sub G. So determine the ultimate capacity by assuming that the piles in the group act as a block with dimension L sub G times L sub G times L. So the skin's resistance of the block is given by this equation. So basically, to calculate the point bearing capacity, we have now this equation, or that is equal to this expression. And to obtain the value of the bearing capacity factor N sub C, it is from figure 9.48. So therefore, the ultimate load is Q sub G, summation of Q sub U now is equal to this equation. Then we try to compare our values obtained from step 1 and step 2. The lower of the two values is the value for our Q sub G. This is the variation for the value of N of C asterisk having the ratio of L all over B sub G and our L sub G all over B sub G. So we have here a sample problem. The section of a 3x3 group pile in a layered saturated clay is shown in 9.49. In the figure 9.49. The piles are square in cross-section. Having this cross-section, the center to center spacing D of the pile is 35 inches. Determine the allowable load-bearing capacity of the group pile. We're going to use Fs equal to 4. Note that the groundwater table coincides with the ground surface. So we have here the equation. So of course, our summation of Q sub U equal to this formula. So we have to obtain our C sub U, which is from figure 9.49, that is 1,010 pounds per square feet, and our C sub U is equal to 1,775 pounds per square feet. And this is the figure for our group pile layered in saturated clay stated in our problem. So for the top layer with C sub U is equal to 1,050 pounds per square feet. So if we try to get the ratio between C sub U and atmospheric pressure, we have 0.525. So similarly from table 9.10, our alpha prime is equal to 0.68. So therefore, our ratio between C sub U and the second layer all over the atmospheric pressure is 0.89. So we get the value for alpha. Alpha 2 now is equal to 0.51 using this. To get your alpha 1 using this value, to get your alpha 2 using this value. So therefore, having those values, we try to substitute now the summation of Q sub U, which is equal to this equation. So we simply have to substitute the values for our value for N1 and N2, then the value for A sub P, C sub U, and of course, alpha 1, alpha 2, and our L sub 1. So we simply have converted our inches to feet. So substituting that one, we get now, simplifying this one, we get 3,141.9 kips. Okay, for piles acting as a group, we have to identify our LG and B sub G. Since the section here identified is 3 by 4 group piles, so meaning to say our L sub G is 4, our B sub G is 3. And we have a cross section which is 14 inches by 14 inches, and the center to center spacing small d is 35. From our discussion a while ago, the formula for this one, since LG is greater than B sub G, so therefore we have to identify our L sub G using the equation here presented a while ago, wherein this one LG is equal actually to N1 minus 1 times D plus 2 all over capital D, 2 times capital D all over 2. So meaning to say our N1 is 4 minus 1, that is 3, times the spacing, which is 35, plus this is plus 2 times D all over 2. So our capital D actually is, we have a cross section of 14 by 14, so our capital D is 14. So you cancel out 2, so we have plus 14. So it gives us 119 inches or 9.92 feet. So our B sub G here actually is from N2 minus 1, so 3 minus 1 is 2 times small d spacing 35 plus capital D, which is 14. So that gives us 84 inches or 7 feet. So this ratio now is equal to 1.42 and 8.57. And from the figure 9.48, we can have our N sub sig asterisk, which is 8.75. So we can now get the summation of Q sub U. So we simply have to substitute that one to the values of our parameters. To simplify, we get now 4,313 kips. And the summation of our allowable, the summation of the allowable pile capacity is equal to Q sub U all over Fs. So it gives us 785.5 kips. So we move on to elastic settlement of group pile. So in general, the settlement of group pile under a similar working load per pile increases with width of the group B sub G and the center-to-center spacing of the pile small d. Several investigations relating to the settlement of group pile have been reported in some literature with widely varying results. So the simplest relation of the settlement of group pile was given by Vesek. So this is the elastic settlement of group pile equal to the square root of the width of the group pile section all over the width or diameter of each pile in the group times the elastic settlement of each pile at comparable working load. Then for the group piles in sand and gravel, for elastic settlement, Mayor suggested this is for group pile in sand and gravel. So our small q is equal to this equation where LG and B sub G, those are the length and width of the group pile section. And N sub 60 is, of course, the average standard penetration number within seat of settlement, which is equal to B sub G deep below the tip of the piles. In SI unit, our S sub G, the elastic settlement, is equivalent to this equation where Q is in kilonewton and B sub G and L sub G are in meters, and our I is equal to this expression. And similarly, for group pile settlement related to the cone penetration resistance, we have this formula. And we have a problem. Consider a 3 by 4 group of pre-stressed concrete pile, each 21 meter long in sand layer. The details of each pile and the sand are similar to that described in the previous example. The working load of the pile group is 6,024 kilonewton, and we are given with this parameters in the previous problem. 3 by 3 group pile, we have our Q allowable, we have which is 502 kilonewton, and our ratio between small d all over d is equal to 3. we have to estimate the elastic settlement of the group pile. So we're going to have this equation. So the elastic settlement is equal to this. We have to identify our B sub G based on our equation a while ago. This is 3 minus 1 times our spacing, center to center spacing, plus 2 times, we're given the cross section. So our capital D here is times D, or over 2. So if we try to substitute, try to simplify this one, it gives us here our value, which is 2.49 meters. Actually, this 3D is taken from here. This is, if we try to have this one, this is small d over capital D is equal to 3. So if you get the value for small d, that is equal to 3D. So we try to substitute the value for small d in this equation. So this is 2 times this d, which is 3 times capital D, so you have your 3D. So we try to simplify this one, it resulted to 2.49 meters. So of course, from example, the previous example, our settlement was 19.69 meters. So if we try to substitute the value for S sub E, which is the settlement, to this equation, you can get the value for our group settlement, which is equal to 52.09 mm. Okay, move on now to consolidation settlement of group piles. The consolidation settlement of group pile in clay can be estimated by using the 2:1 stress distribution method. We have learned this in soil mechanics. Calculation involves the following step. One is, let the depth of embedment of the pile be L. The group is subjected to a total load of Q sub G. If the pile cap is below the original ground surface, Q sub G equals the total load of the superstructure of the piles minus the effective weight of the soil above the group pile removed by excavation. 2. Assume that the load Q sub G is transmitted to the soil beginning at the depth of 2 over L. 3. From the top of the pile as shown in our figure, the load Q sub G spreads out along 2 vertical to 1 horizontal line from its depth. Lines A prime, and B prime are the 2:1 line. So calculate the increase in vertical stress caused at the middle of each soil layer by the load Q sub G. So the formula for compute for the increase of the vertical stress is given by this equation. So this is the illustration showing to us the consolidation settlement of group pile. This is our the load acting on the group pile. So you have here 4 layers as illustrated. So basically, the spread here of the stress is having a theory of 2:1 method. So for calculate the consolidation settlement for each layer caused by the increased stress, this is the formula that you're going to use. Wherein you have the consolidation settlement of layer I. This is void ratio, change of void ratio caused by the increase in the stress in layers I. And you have the initial void ratio of layer I and the thickness of the layer I. Then you have to compute for the total consolidation settlement of the group pile given by this equation.